back to talk about Le Chatelier's principle today. Let's say we have an equilibrium reaction like this right here, and N2 combined with H2 yields NH3, yields ammonia. And so this would be a typical graph for a reaction like this. A graph of the reaction rates as they head towards equilibrium. We start with high forward reaction, and the reverse reaction slowly increases, and eventually over time it reaches this state of equilibrium. Well, what if we had something happen like this? What if at 80 seconds we add more reactants, and maybe we add more N2, for example, okay? Well, what's going to happen when you add more N2, that's going to increase the concentration of N2 on the reactant side. And so all of a sudden there's going to be immediately more forward reaction, right? Because there's more of this present in the system, and it's going to move forward. And so we're going to have this at the top here, this forward reaction start. But as the forward reaction starts, it's also going to begin to produce more reactant, right? So at the same time, as that starts really high, we're going to have slowly an increase with the reverse reaction, and then eventually we're going to get a new equilibrium, right? And so this is the time here, like in this graph, around 80 seconds, right? This was the time that more reactant added, and so then it eventually reaches a new state of equilibrium. Okay, so this process here, Le Chatelier's principle, kind of deals with that topic, and so that's what we want to talk about with the time that we have in this particular lecture. What is Le Chatelier's principle? It describes this phenomenon where when you add a reactant or a product to a chemical equation, a chemical reaction that's taking place, what's the result going to be? We'll do this with a black marker, so it'll be a little easier to read. So let's give you a definition for Le Chatelier's principle. And it basically says, make sure you know this, when a chemical, when an equilibrium is stressed, and by stressed we're talking about like when we added reactant to the system earlier. When an equilibrium is stressed, it will shift in a way that relieves the stress and reestablishes equilibrium. And that's what we saw with our graph, right? The reactant was added, and sure enough, the forward reaction increased because more reactant was added, but it shifted towards a state where more reactant was created, and so that reaction rate came up, and then we reached a new state of equilibrium. So Le Chatelier's principle deals with that. Like I said, stress is when the concentration changes on one side of the chemical reaction, okay? And so based on what we saw in our graph, the way the reaction immediately shifted to try and overcome that increase in concentration on one side, and then eventually reach that new state of equilibrium, we can make a couple of comments about that. And so we can basically, a couple of observations, and so we can say this, that in general what's going to happen is that an equilibrium will shift away from the side of the reaction that experiences an increase in concentration, right? When we increased the concentration on the reactant side, what happened? The forward reaction then was it all of a sudden, increased dramatically, and the result of that was that the reaction moved towards the product side, right? Shifted towards the product side. So conversely, it will shift towards the side that experiences a decrease in concentration. Right, and so, like I said, that's the opposite kind of the first statement, right? But it makes the point that if instead of adding something and increasing the concentration, we may affect the chemical reaction by removing something from the system and therefore reducing the concentration on one side. So if we reduce it on one side, the reaction is going to shift towards the side that experienced that decrease in concentration. All right, so let's do an example on page 496, example 16.5. And this problem gives us a chemical reaction, says the following equilibrium is established. And so 4Cu plus in aqueous form plus sulfur in solid form plus 3H2O in liquid form is going to yield 4Cu in solid form plus H2SO3 in aqueous form plus 4H plus in aqueous form, right? It's an equilibrium reaction. And so given that reaction, the first question is what will happen to the concentration of H plus, right? So what's going to happen to this concentration if more Cu plus is added, right? So basically Cu plus, the concentration of Cu plus is going to go up, all right? So what did we say with Le Chatelier's principle? It's going to, the reaction is going to react in such a way to relieve the stress. And so the statement that we made, that we derive from that is that whenever there's an increase in concentration on one side, the reaction is going to shift towards the other side and make more of whatever's on the other side. Okay, so in this case here, if Cu plus goes up, the reaction is going to shift to the other side of the equation, to the product side, and therefore H plus is also going to increase. All right? The next question says, what will happen to the concentration of H plus if H2SO3 is removed? All right? So if H2SO3 basically, so the concentration of this then is going to go down. So what's going to happen to H plus if this concentration goes down? Again, the statement that we made based on Le Chatelier's principle was that if concentration goes down on one side, then the reaction is going to shift in that direction, toward the side where there was a decrease in concentration. So again, this reaction is going to shift towards the reactants, and just like we saw last time, when this increased, when this decreases, H plus again is going to increase, right? The concentration of H plus will increase. And then finally it says, what will happen to the concentration of H plus? We're interested in H plus again. What will happen to the concentration of H plus if more S, sulfur, solid sulfur, is added to the reaction? And the answer is, for this particular one, nothing. Why is that? So if you remember, whenever we considered the equilibrium constant, we said that you can ignore solids and you can ignore liquids, right? Because the concentration is not going to be affected by the solids or the liquids. So you just totally ignore those when you're figuring the equilibrium constant. And so it shouldn't surprise us that they also don't affect this at all. It has nothing to do with the equilibrium in the system. if we add or take away something that's a solid, if we add or take away something that's a liquid, okay? So if we talk about the concentration of something else, it's unaffected if it's a solid or a liquid that's adjusted in the system, okay? All right, that's it for this lecture. We'll see you again before long.